We're going to look at sine functions, and we'll do a little overview of what I used to have the word sinusoidal here. We'll talk about what a sinusoidal function is, and then we'll dive right into a sine function because it's a very common function that we usually use to represent sinusoidal relationships. And sine you'll have seen maybe with trig when you're doing like SOHCAHTOA, I mean opposite over hypotenuse, okay? But it's interesting because the values of sine when graphed out over time build like a wave. It looks like a wave, and that's what sinusoidal functions are. So for something to be sinusoidal, it has to kind of follow a pattern, okay? So this has got like a wave pattern to it. It's actually technically known as periodic also, but sinusoidal has this wave to it, where periodic could be something like this. See how I have like kind of straight lines here? These straight lines wouldn't be sinusoidal. They'd be periodic because it repeats. If you notice, like if we start from here to here, that's the same pattern. It makes this like S, sideways S, best way to describe it, I guess. But because it's so jagged, it's not sinusoidal. It's not a wave-like. Where sinusoidal is this wave-like thing, okay? So anything that repeats is periodic, and anything that repeats in like a wave-type fashion, that's sinusoidal. And then within those things, we can even talk about some of the very important parts of them, okay? In fact, what they're going to have is, this is a maximum, okay? That's the top of something. It's also known as a peak. Sometimes the stock market refers to things like this, like a peak of something. And the bottom, in mathematics, the easiest way to represent it is calling it a minimum. But sometimes they name it a trough, T-R-O-U-G-H. I think that's how you spell that. It just means the bottom of a wave, okay? So any of those is fine. There's a max, there's a min. The difference from the max to the min is known as the range. So the range of something. Let's say that this is, oh, I don't know, 2, and the minimum is -2. That means the range would be 4 in this case, okay? And there's technically an imaginary line that always runs through these wave functions, okay? Right through the middle. And this is known as the equation of the axis. EOA is a very common like initials to use for it. And the way you can find the EOA, I'll say EOA is equal to, we'll say max plus min divided by 2. It's, in other words, it's the average of the maximum and the minimum, and the average of the top and the bottom would always be the middle of something. That's essentially that idea, okay? To find the range, these are little equations you'll have to know throughout this. The range is the max minus the min. That's all that is. It's just the top minus the bottom tells you the difference between the two. So common ideas, but we just given different titles to stuff to help us remember them. Okay. There's also something called an amplitude. The amplitude is the distance. This is an interesting one. Do I have more colors? I need more colors for this. All right. Like there's a purple. Oh yeah, there we go. Oh, I got rid of my black. Oh, nuts. Oh well. The amplitude is the distance from the middle to the top or the bottom. It would actually be the same. Since it's the middle, just like a circle, anywhere from the middle of the circle to outside of the circle is the exact same. So they call this the amplitude. Okay? So we usually refer to it as I'll talk about how the amplitude relates here. I should have used better colors that match back to our equation a little nicer. Amplitude is the difference from the top to the bottom, and there's two ways to calculate amplitude. It can be the max minus, oh nuts, I got rid of my black. I'm going to bring it back here. All right. Max minus I needed that yellow. It's not working out for me, these colors. The equation of the axis, or you can have the equation of the axis subtract the minimum. It's technically the exact same thing. You're just finding the difference between those values, okay? All little formulas that help with the idea of periodic functions or sinusoidal functions. And then these ideas actually help a lot when it comes to problem solving. When we get into the transformations of sinusoidal functions, we really don't pay attention to any of these at all, but they're very helpful little formulas when it comes to problem solving, because when they start talking about wheels and things over time, these really become handy, okay? So we did a quick review of sinusoidal and periodic functions, and now we're going to talk about the sine function very quickly, okay? So that's not working. What's going? Oh, there we go. So nuts. I want the whole page. All right, that was way harder than it needed to be. So put that in the corner there. A sinusoidal function. Let's say we're gonna draw it on a graph. Okay. We usually refer to it. Oh my, that's not what I wanted. We usually deal with it in terms of degrees. Okay, so the x-axis here is measured in degrees, and the y-axis is just measured in usually a unit of 1 or 2. Okay, so let's do this. This will be 1, and this will be -1, and obviously the middle is 0. I'm going to quiet the dog down for a quick second. Shh. No. Quiet. Close the door. In terms of our degrees, there are 5 really important ones, okay? And if you think of a circle, some really important degrees, if we draw a cross through them, are like 90 degrees, 180 degrees, 270 degrees, and then technically this is 0, but it's also 360 degrees, and we go full circle, okay? So I'm going to put them in here. Let's say that's 90, 180, 270, 360. Okay, for sine, it's really specific the way this graph is drawn. At 0, so this when we're at 0 degrees, we're at 0. Okay, we're also at 0 in terms of the height. When we get to 90 degrees, the y value is 1. So we're going to call this x value is 90 and the y value is 1. That's an important coordinate to memorize for a sine wave. Another important one is when we get here to 180. 180 is back at 0. And think of this as if we're going around a 0. Around a circle. How far away are we from this horizontal line I've drawn? Okay, so we'll say this is a unit circle. A unit circle means that the radius is equal to 1 unit. Okay, so if I travel around this circle, when I get to 90, I'm 1 unit away from this horizontal line, okay? So squiggly. So that's how far that is. That's 1 unit. Then when I travel back around the circle, I'm actually back on this horizontal line. So I'm at 0 again. So we're representing going around a circle over a period of time, okay? Now I know technically it's degrees, but we're lengthening degrees as if we can continuously go around a circle. Next, when we go to 270, I'm 1 unit, except that I'm 1 unit below the horizontal line. So this is known as -1, okay? So this value here is x is 270 in degrees, and the y value is -1. That's your y and that's your x. And then finally, when we come back to 360, we're back on that line again, so we're 0 units away. So I take these 5 major points, so 1, 2, 3, 4, 5, and this is a period. A period of the function is how long it takes for something to repeat itself. So I could continuously draw this again. The next important point would actually be 450, and then 540, and then 630, and then 720s over there. So I could repeat this. This would go back up to 1, to 0, there, to there. And this would continue as long as I just kept going around and around this circle here, okay? The period's important. The period of a function, I didn't define it before, but the period is how long along the x-axis it takes for something to repeat. So the period of a sinusoidal function happens to be 360 degrees. But if we were back up in these periodic functions, I didn't give us any x values, But a period would be like from here to here on that red function I drew. And in this wave function, from this minimum to this minimum, however far that is the period of the function. Okay, so that's the visual for it. Now, once you know the basic sign, especially these 5 key points, we can kind of just transform the equation from there. And what we mean by that is we can stretch a sinusoidal function. A sinusoidal function can become far more, I can become far more pronounced, like going up like that and down like this and back to the middle. It can be shifted. It could be the same height and stuff, but like kind of shifted over by a value of by a value of something, or it can be shifted up and down. Maybe it's been just moved up like this. So it can be anything like those. Okay, I'm gonna take those away, and then what we'll do is we'll go on Desmos to talk about all those transformations. But what's important here is this original function I drew. It's actually similar to when we did quadratic transformations. The a value, okay, sine x minus c plus d. Oh, I lost my green. I don't think I need purple anymore. Okay. So the a value has to do with vertical stretches. Okay. And it's usually easiest to apply the vertical stretches or compressions. It can actually, I could technically draw something like this that's far less pronounced. It's not going up as much. There you go. So it's vertical stretches or compressions. Just like in the quadratics that got thinner or wider, the same thing happens with these. They can get like pulled. Think of it like an elastic band being pulled up or being squished down towards something. The C value deals with horizontal translations is usually the word. So horizontal translations. That just means moving something from left to right. And the green one is vertical translations. So that means we can move that up or down. I am going to very quickly there it is. I'll open Desmos here to give you an example of what we mean by that. So let's say I need to spell out S-I-N, sine, bracket x, subtract, what do we say, C? Yeah. C plus D.
Oh, it's the same, thing?
You can put any letters you want into decimals.
Oh, no, separate, it doesn't, it's...
Yeah, so here in your textbook, they've given you them separately. I'm putting them all into one, so we can see them all at one time, okay? So I'm going to say all right now. And I actually want the A value, I want the C value to be 0. And I want the D value to be 0 also, okay? And this needs to be put into degrees. And it needs to be far wider, because remember it goes to 360, so I'm going to go 720. And then the y-axis really only needs to go from like -5 to 5. All right, so we got a much better view now. So we take a look, 1, 2, 3, 4, 5. Remember those 5 points I talked about? 0, 0, 91, 180, 0, 270, -1, 360? I put in a sine function. I could draw it in again here. It's just sine x. That is sine x, with the a value being 1, right? If a is 1, it doesn't do anything. If c is 0 and d is 0, that's the original function. If I start to stretch a and make the number larger, you'll notice these points at 0, they don't change. They're always cutting through there, but the peaks or the max and the minimums have become far more pronounced. In fact, if a is 4.7, the y value is 4.7. This is known as the amplitude. So whatever a is actually what the amplitude is. So let's bring it up to 10. Zoom out just a little. So you notice our amplitude's all the way up at 10, positive 10, and negative 10. Okay, so that gives us a little information. Let's bring this back. And if I go below 1, not quite 0, but if I go between 0 and 1, notice how they're less pronounced, like it's only 0.6. If I go to 0, we're going to get nothing, a flat line. And if I go to negative, it actually inverts them. So where it normally goes up, it actually now comes down. Still, the absolute value is the same. If I go to negative 10, it's going to be down 10 and up 10. But where a sine function normally goes up from 0, if it's negative 10, the a value, it actually goes down from 0. Okay? So let's bring this back to 1. 1 is the standard. Go back to 1, machine. There we go. C, we said, was horizontal shifts. So I'm going to need actually bigger steps here. Step needs to be from like 360 to 0. Actually, no. We're going to go from 90 to 0 because we're going to talk about this. 90 being important. Okay. So you notice as I start to move this, it starts moving to the right.
Mm-hmm.
In fact, if I go all the way... Oh, 90 wasn't far enough. What am I thinking? 180 is what I need to go to. There you go. 90 is like kind of at the halfway point, and if I go all the way to 180... Oh, it is 360. I don't know. Let's go back. There we go. At 360, it actually ends up exactly where it was before. Okay? Mm-hmm. So it kind of gives you the idea of 360. So at every 360 interval, we actually have the same visual. It looks the exact same. The only difference is it technically is shifted to the right. Your C value here, if I put sine x and I type in sine, I need a bracket, x plus 360. Watch this. I don't want that to be that either. It drew it right on top. Even though sine x and sine 360x are different equations, they're drawn right on top of each other because it's a 360 degree period. That's the idea I've been trying to give you here. Like if we shift it 360 degrees to the right or left, it just overlaps the original one because it's a periodic function. It repeats itself over and over and over again. Okay? And finally, let's go back to 0 here. D. D is this vertical translation. So it moves the equation of the axis up. So if you look at this, it looks like there's a horizontal line through the middle at 5. That's what our D value is. So the equation of the axis is actually equal to D. Okay, so I can move this all the way up to 10. The middle would now be at 10. All the way down here, the middle is at negative 10. And 0, which is normally the equation of the axis, is the normal sinusoidal function. So let's kind of relate these two things back. Oh, I need purple again. Nuts. Here we go. Your A, which is the amplitude, okay? Whatever the A value is actually the amplitude of the function. We know that. And the D value, we just said, was actually the same as the equation of the axis, okay? So whatever the equation of the axis is, that's actually what our D value is. It's the horizontal shifts that we don't have like an exact formula for, but that's essentially it when we go to transform these things. Now we can do it by hand and stuff, but it's very neat, and as most it becomes a little simpler. I'm going to take a picture of what we've done here. I'm going to move this over 90 degrees. That's a lie. 180 degrees. I'm going to bring the amplitude up to 3, and I'm going to shift it up 5 units. So very different here. That's a pretty different looking function. Yeah. Okay, and the steps we went through, I'll show you each of the steps. We start at sine x. I'm going to then stretch this. Remember, we put the a value here by a factor of 3. Okay, so that was your a value. Your amplitude now went to 3. I'll change the color on this so it's a little nicer to look at. Actually, you know what? We'll do it as dots so you know these are steps. So the first step was to increase the amplitude. Okay, the next step, 3 sine bracket x. Let's say we do a horizontal movement. The horizontal movement would be minus 180 degrees. Should be a 3 here. Didn't I put it in? I thought I did. There you go. So notice the blue one has shifted 180 degrees. It's like right in between where it was before. And finally, the last step, I think I can just copy, can't I? Duplicate, there we go. Getting smarter in life. The last one we added up by 5, so D plus 5. No, I'm not going to keep that. We'll make that purple dots, and This one will be blue dots. So we know that they're shifts. So we start at the black line. We move to the green line, becomes more pronounced. From the green, we go to the blue. We shift it 180 degrees to the right. Even though it's negative, we shift to the right. Just like in quadratics, negative is to the right, positive is to the left. And then finally, we go up 5 units. So the equation, the middle of this, moves up to the 5 here. Okay?
Okay.
That's the general idea of sinusoidal functions.
Can I have a picture of the first page you
Yeah.
initially? Okay.